Hi guys, good morning. As you can see, the background is changed. It is neither the background of Bangalore nor the background of my hometown. It's a background of a hotel I'm staying in Allahabad because Arch, your voice convocation is there. And yeah, we'll see this problem. Let's see. Basically, I started the recording and then my laptop screen went blank. You will see the upcoming vlog that how it just goes blank because that's the reason I use monitor. But yeah, without further ado, let's start with the question, not skip the question. We are having a reference node in a connected undirected graph. Reference node, which means a starting node. Cool. Connected undirected graph, which means one graph, as we saw in our bar graph series. What is a connected graph? So in that we also saw okay, one connected component is a connected graph. Cool. Undirected, which means bidirectional edges. We have to read a deep copy, which means a deep clone of that graph, which means that if I have a node right here, let's say A, if I have a node right here, I have to make a clone, another clone, let's say A dash. If I have A to B a node, I have to attach a node B dash such that A dash and E dash are connected. That is actually a deep copy. Cool. Now, each node in the graph contains, it is just showing how a node is being represented. As in the graph series we saw that there are four ways to represent a graph. It is the second way, what we saw, that a graph can be represented by just writing down the node and the edges. It's not the only two ways to represent the graph. There are four ways to represent the graph. And it is the second way which we saw in our bar graph series that okay, how the graph is being represented. It's very simple, a node and all its neighbors. Cool. Which means that if we want to make a new node, let's say a copy node, so I will have that copy node which will actually have the value of the node and also all the neighbors. That is how a graph is being made. Now, as I showed you, how a clone is being made is I have, let's say, an original node, let's say one. I have to make exactly the same node with the same value. I have to make exactly the same node with the same value, but a new node. I made a new node one. As you can see, it's a different color. As and when I make a new node, if I am using same node, it will be of the same color. If I'm using a different node, it will be of different colors. That's the reason I have used colorful things in this. It was very hard to make, but yeah, I think it will be worth it. For the node 2, I made exactly a replicate value 2, but a new node. And also, I have to make sure that I make this exact graph because you can see the old node 1 and 2 are connected, so the new node 1 and 2 should also be connected. That is the reason it is a clone graph. So now you understood okay what a clone graph looks like. It's also in the explaining the question that okay, a graph is there and a clone graph should not have exactly the same nodes, which means the nodes here are same, but I just want the values to be same, but the nodes should entirely be new, which means as you can see here the node is entirely new. It's in a blue color, which means a new node. Why here it's a yellow color, which means old node. So I'm not saying to actually replicate the addresses also. I'm just saying grab the value, but make a new node out of that. And as you can see, that order also remains same, exactly same. It's just replicating, but a new replication. As it is showed, but you'll see actually what we have to do. So basically, it's just a simple problem of cloning a graph, tree, linked list, etc. It's all the problems are exactly the same. It's just that what we have to make sure is that we traverse on that whole graph. In linked list, you traverse on the whole linked list. In tree, you traverse on the whole tree for everything. Mark my words, for everything, graph, tree, linked list, anything. You use the same procedure. You just traverse it. The word traverse in graph, we have two traversal techniques: a BFS and a DFS. We also saw the same in our graph series, map graph series. But and we have to copy. We have we have to copy each node, and basically when we copy each node, then what happens is okay, a copy is made. We traverse a graph, a copy of this node is made, but then I also have to make sure that whatsoever copy of the next node is made, I also have to attach those copies made. That is simply what a clone would look like. Let's see the example. If we have this original graph, which is in the question itself, and we have to clone this graph, we have to clone this graph. So the clone graph will look something like this. As you can see, one is here in yellow color, but the one here is in the orange color. The two here is in the pink color, but the here two is in a red color. Here the four is in blue color. Here the four is in green color. Thus, it is being showed, okay, for one, I just grabbed that value one, but I also made sure that, okay, my two, it should be the new one. It's a new one. So the neighbors of the orange one are not the pink one and the blue one. It is the red one and the green one. That is the reason what we will make sure in a clone, how a clone should look like. Let's see how we will make this clone. So basically, every node, as I said, every node I have made a different color, but as we saw that we have to traverse this whole graph. And and as we saw, for every graph node, wait, बहुत शांत बैठे. For every graph node, I have to I have for every graph node, I have to actually make a corresponding clone node, right? So I have to also make sure one thing that I should make sure, okay, for this node one, the corresponding clone node which I have made is actually like, let's say, one dash, because in future when I'm going on to two, I should also be knowing, okay, if I am moving from one to two, I have to move from one dash to two dash. Now to actually know that I have to move from one dash, I should be knowing, okay, for one, the corresponding clone was actually one dash. So it's that, okay, if I'm moving from one to two, so the corresponding movement will be one dash to two dash. But to actually know one is as equal as one dash, we have to make a map from actually node to a clone node, which is one dash. It's the reason to actually traverse, we need a corresponding clone node for every node. As we are making for one, I'm making a one dash, right? One dash is simply a node with a value one, but actually a new node. I'm just saying for that reference. Now, okay, we make a map for from node to a clone node to actually traverse on that graph. As we saw, traversal is from both a BFS and a DFS, but I am actually explaining you why a BFS. A DFS is also exactly the same. The code is short, but it is much easier to understand via BFS. Although I always say, if in any algorithm, if both a BFS and DFS is being applied, a BFS is a bit lengthier and a bit longer to write. But here in this case, I will just recommend to start with BFS because it's easy to understand what actually is happening. Because this cloning thing will actually make you confused very much. So it's the reason I'm starting with the BFS. What happens here in a BFS? You start with a node, you explore all its neighbors. Then you start with this neighbors, you explore all its neighbors. This is what happened in BFS, right? So I started with one. I make a clone of one. One has not been, because I'm starting right now. Nothing has not been made right now. So I am starting at one, yellow one, which is the original one. I make a clone of that, which means the orange one. For two, I know, okay, my original one node has the neighbors two and four, which means the pink two and the pink and the blue four. So for this one node, the neighbors have not yet been explored, which means I have not made a 2 or a 4. So I need to make, mark my words, I have not made a 2 or a 4. Mark my words, I have not made a 2 or a 4, which means I will just make a 2 and I'll make a 4. But how, Aaron, will you know that you have not made a 2 and a 4? Either you can have a visited array, another a map, basically. But you are also making an unordered map, right? As I showed you from this corresponding node to a clone node. If you actually know, okay, I have made the clone of this node, which means it is visited. As simple as that. So this corresponding clone, which means the map which you are using from node to clone node, you can actually use this to actually know, okay, if this node has already been cloned or not. For the node one, as I was starting, it was already not cloned, so I cloned it. For the neighbors, I saw, okay, 2 and 4. Are they cloned? No. So let's clone them also. So with this, I just put in my map, okay, 1 is cloned, a 2 is cloned, and a 4 is cloned. Right now, cool. But I also have to make sure after cloning 2 and 4, I actually know, okay, for one, the neighbors were 2 and 4. For this new one, the new neighbors are cloned 2 and cloned 4. So I actually have to say, okay, my cloned 1 has the neighbors as cloned 2 and cloned 4. I'll show how, what we did. Firstly, we made a copy of a node, which means firstly, I just have this old one, which is this node value. I made a copy of this one, which is the new one, which means a copy of this node is being made. Now, this copy node is actually a one node, which which right now has no neighbors. It's just empty as a orange. It has no neighbors right now, but it actually has a value one, which is actually a clone of one. Now, I actually know, okay, I have made a clone. So I have to update my map because my map actually is a copies map. I will have in my code a copies map, which actually will have a map from a normal node, which means a normal node, to a new clone node. So I just had a, okay, it's, you can see a normal node and it's a clone node. Okay, I have this map, which is actually letting me know, okay, if this node has been made or not. Cool. Now, as I said, I also have to make a clone of the neighbors if condition will always be there before this line in the code if you will go and see the code. But let's assume that, okay, the neighbors are not made. So I'll just make what? I'll just make the new neighbors. I just make a new cloned node of those neighbors. See, it is the neighbors of my one, which is 2 and 4. It is the neighbors. I just iterate on my neighbors. I just have this neighbors. It is the old neighbors. It is the old neighbor. It will actually make me a new neighbor, new cloned neighbor, new cloned neighbor. Now, actually, I have to also update, okay, this 2, which is actually the old neighbor, it should map to a new neighbor 2, because I'm just mapping my old values to a new values to actually make sure, okay, I have made a clone, because I don't want to make a clone again and again. I don't want to visit the node same again and again. So I just wanted to say, okay, my copies is it's actually made, and it's actually saying, okay, my copies will actually is the this copies is actually the new node, which will actually be mapping. See, it is the old neighbor and it is my new neighbor. So it is just mapping my old neighbor to a new neighbor. That's it. Now, as also said, okay, my node is made, my new neighbors are also made. See, my node is made, my new neighbors are also made. We are forgetting one thing, right? Attaching the new neighbors, right? From new node, I'm attaching the new neighbors also. So I'm just doing the same thing. From my copied node, which means the copy which I have made, I'm just attaching my copied neighbors. And as I'm saying that my copies, which is a map, which actually we store from node to a copied node, from neighbor, sorry, from neighbor to a copied neighbor. It is just a mapping which will actually help me to actually figure out, okay, from, because see, I am only able to iterate on my original map, right? So from this original map, I know one is mapped to two. So I have to map a copy of one to a copy of two. With this help, I can actually do. So my this map is solving two purposes. One is to actually make a attachment from one to two. I need to attach. So I'm attaching from one dash to two dash, and it's also making me sure, okay, it is that node already made or not? If it is not, I'll make it. If it is already made, so I will not make it. It is the only thing which you have to do in this question. Now again, as we traverse on this graph, see, one is visited, one work is done. Now comes the work of next node, which is two. So again, I went to two, but you remember one thing, two was already made via the one's neighbor. When we are iterating on the one, so the neighbor of two, the neighbor of one were two and four. Two and four were not made already, right? So I just made a two earlier only. So I don't have to make it again. With because I know because of my map was saying, okay, you have already cloned two, you don't have to clone it again. But maybe its neighbors were already cloned or not. Let's see. I will just go. Neighbors of two are one and four, one and three. One was already cloned. So okay. I just have one cloned. No worries. One is already there. 3 was never cloned. So I'll just clone a 3 right now and there, and I will just have a 3 cloned with me. Also, with this previous graph, I know, okay, a 2 is attached to 1 and 3. So I'll just attach the cloned 2 with cloned 1 and clone 3. Made the 3 I made right now, but the 1 was already made, and the 2 was already also made. Cool. Next, I just iterated on my, see, when we are moving in a BFS, we move from node to node to node. Although if you started from one, so you had this two and four, but I just okay skip. Okay, I just iterated on two, but I just skipped four because it just as same as two. But then ultimately you will also land into three because as we are on two, so we will push three. But actually the four should have been there. But actually I'm just iterating on three to actually show you how in the last it should look like. So actually, what will happen? Three already cloned because of the neighbor of two, and its neighbors, which are two and four, they're also already cloned because two was already cloned. Four was cloned because of the one neighbor. Okay, three's neighbors, which is two and four, are already cloned. Which means okay, now my only task is to attach the neighbors. Which means I will just attach the clone three with a clone two and a clone four. That's the same thing you have to do. Let's see the code pretty quickly. It's pretty simple. Exactly the same thing what we did. Exactly the same thing. What thing I showed you right here, right? These four steps. These are the exact four steps which you have to do. Exact thing. Like I'm not changing anything. We just if condition as I said will be applied here and that's it. Let's see the code pretty quickly. Firstly, a very base case. Okay, if my node is already null, you can just not even start the graph itself. Just return a null. As the base example itself says, okay, if it's null, just return a null. Next, I have this unordered map of copies which actually store the copy from the original node to a copied node, which will actually help me know, okay, what is the copy, if the copy is already made or not, and also will help me to actually move from one to two to a copy of one, which is one dash to two dash. I will actually make a first node copy because it is for sure we are starting a graph which it is already not made. So I'll just make a first node copy. Then I will just mark in my map also, okay, it's a node and it is its copy. I will just mark it the same thing. Then a standard BFS where you push in the first node, you do okay, while this queue is not empty, you just grab the first element of the queue, you just pop it out, and now the actual fun part starts. I'll just iterate on all the neighbors of the original node, which will actually help me. Okay, I'll have to iterate on them. I'll just see if that node, which means right now I'm iterating on neighbors, right? So I'll just check if that neighbor copy is already made. If that neighbor copy is already made, if it is made, so why to make it again? If it is not made, then I'll just make a copy of that neighbor. Firstly, I'll just grab that neighbor value and I'll just mark it. Right now it has no neighbors at all because I'm just making a copy. That's it. I'll just make its new copy of the neighbor because the neighbor was already not copied. Now, as it is copied, I'll just push it in queue. Cool. Now, even if it is copied or not copied, good. Not copied, I'll just make a copy. But even if it's copied or not copied, I actually have to make a connection, right? Ultimately, we have to do that task. Here it is I what I'm making connection. As I showed in the last step also. Here I was making connection. From the node, I'm just grabbing the copied node, I'm just connecting my copied node to actually my copied neighbor. That's the same thing I'm doing here. I am just grabbing my copied node or clone node to I'm just neighboring, pushing like putting the neighbor as the clone neighbor. And ultimately I just return the copy head, which is a simple copy. DFS code is also very easy. It's just that simple steps. See, as you can see, the code of BFS is pretty huge, right? DFS code is pretty small. That's the reason I always suggest to write a, a DFS code. Let's see it pretty quickly. Exactly same. A null condition. If it is null, then just return a null. Then I'll just ultimately see, okay, if that node is already copied or not. When I say node in a DFS, I'm actually referring to the whole DFS subtree which happens because a DFS moves from here to here to here. So when I'm saying, okay, if it is copied, which means its whole subtree is copied or not. Okay, I'll just say if it is copied. If it is not copied, then actually I will make a copy. And here also I'm just using the map to actually because ultimately I have to iterate from one. I have to iterate to one dash. Like from one, I have to go to okay. From one to if I'm going, I have to also need to make sure I go to from one dash to two dash. Then if I just make a new copy and also I just grab this particular neighbors of that particular node. Okay, this node has what all neighbors. I'll just, as it is a DFS, so the node making part is already done by this particular thing, because in a DFS, a new node is already made in the DFS subtree. Ultimately, I just attached my node to its copied neighbor, the copied node to its copied neighbor, and that's it. The rest of the part is done by the DFS step itself, and it is nothing we have to do. It's the reason. It will actually be recursive. That's the reason. If the people are not familiar with the DFS, if you are not much good with it, so you might be having some issues. Okay, how to figure it out? But it's the reason I explained with the help of a BFS, which is actually iterative, and you don't have to worry about anything at all. And yeah, time complexity will be nothing but A into B, because you are iterating on every edge. Basically, for every node, you are having what? The all the nodes which are connected to it, which are actually the number of edges. For this node, I am, let's say, having node 1, 2, 3, 4. So if it is connected to every node, so I'll just have every node into it. One is connected to 2, 3, 4, so I'll have 2, 3, 4, and same goes for it. Let's say for two, if I have 1, 3, 4, so actually it will go on to every of its neighbor, right? That's the reason it is E into V. Space complexity is also E into V, nothing but making the graph itself, because we have to make a clone graph. So, and using the unordered map from the original node to the actual copied node, and also the queue of BFS, or even if you use a DFS, then also a recursive stack internally is being made, which will actually give a complexity of V. In total, it's E into V. You don't have to worry about it. The code of both C++ and Java of both BFS and of DFS is given below. You can just have it checked. And as I said, it's a pretty good question. It's the most generalized thing you can see. Whenever you have to in future iterate on the anything, you have to make a clone of anything, linked list, doubly linked list, graph tree, anything. Just traverse on it. Just make sure you have the connections mapping. Okay, because from if you're moving from the node A to node B, even in the linked list tree, anything, or a doubly linked list, you should be knowing. You should make sure you should be knowing. Okay, you're moving from A to B, so you have to move A dash to B dash in the copied or the deep copied graph, node, tree, etc. That's the reason I just try to explain it more intuitionally, and these steps which are actually required, because it's nothing but the same thing for everything. Same thing for everything, what I'm saying. But yeah, that's the reason where the steps go on. Yeah, these process, that's the reason I just told you. Every time you have to just follow these steps and you will be good to go. I hope that you guys enjoyed it. I know the picture quality is pretty bad because it's being recorded from my phone, like laptop's camera. And I'm just using a flash of my phone's camera, as you can see right here, because the lighting was also pretty bad. So yeah, that's all from me, and I hope that you guys liked it. If yes, then do the like button and see you in the next video. Goodbye, take care.